Hi and welcome to Computing Fundamentals 2. In last video we have defined and discussed what do we mean by binary trees, decision trees and the prefix code. In this video we will focus on the following topics: traversals, algorithms, and infix, prefix and postfix notation. Order-rooted trees are often used to store information. We need procedures for visiting each vertex of an order-rooted tree to access the data. We will describe several important algorithms for visiting all the vertices of an order-rooted tree. Order-rooted trees can also be used to represent various types of expressions, such arithmetic expressions involving numbers, variables, and operations. The different listing of the vertices of order-rooted trees used to represent expressions are useful in this evaluation of these expressions. Procedures for traversing all vertices of an order-rooted tree rely on the orderings of the children. In order-rooted trees, the children of an internal vertex are shown from left to right in the drawings representing these directed graphs. We will describe one way we can totally order the vertices of an order-rooted tree. To produce this ordering, we must first label all the vertices. We do this recursively. First, we label the root with the integer 0. Then we label its k children at level 1 from left to right with 1, 2, 3 up to k. For each vertex at level n with label A, label its kv children as they are drawn from left to right, with A1, A2, AK of V. Now, following this procedure, a vertex V at level n for n greater than or equal 1 is labeled x1, x2 up to xn, where the unique path from the root to V goes through the x1 vertex at level 1. The second vertex at level 2 and so on. This labeling is called the universal address system of the order-rooted tree. We can totally order the vertices using lexicographic ordering of their labels in the universal address system. The vertex labeled x1, x2, x of n is less than the vertex labeled by y1, y2, y of m. If there is an I greater than or equal 0 or less than or equal n, with x1 equal y1 and x2 equal y2 and so on. The following example illustrates this. We display the labelings of the universal address system next to the vertices in the order-rooted tree shown in figure 1. Now let us discuss one important topic of computing, which is traversal algorithms, and those are used heavily in networking and transmission and communication systems. Procedures for systematically visiting every vertex of an order-rooted tree are called traversal algorithms. We will describe three of the most commonly used such algorithms: pre-order traversal, in-order traversal, and post-order traversal. Each of these algorithms can be defined recursively. We will first define a pre-order traversal. The viewer should verify that the pre-order traversal of an order-rooted tree gives the same ordering of the vertices as the ordering obtained using a universal address system. Figure 2 indicates how a pre-order traversal is carried out. Example 2 illustrates pre-order traversal. So let us take an example. In which order does a pre-order traversal visit the vertices in the order-rooted tree T shown in figure 3? The steps of the pre-order traversal of T are shown in figure 4. We traverse T in pre-order by first listing the root A, followed by the pre-order list of the subtree with root B, the pre-order list of the subtree with root C, which is just C, and the pre-order list of the subtree with rooted D. The pre-order list of the subtree, which root B, begins by listing B. then the vertices of the subtree with the root E in a pre-order, and then the subtree with the root F in a pre-order, which is just F. The pre-order list of the subtree with root D begins by listing D, followed by the pre-order list of the subtree with root G, followed by a subtree with root H, which is just H, followed by the subtree with root I, which is just I. The pre-order list of the subtree with root E begins by listing E, followed by the pre-order listing of the subtree with root J, which is just J, followed by the pre-order listing of the subtree with root K, and the pre-order listing of the subtree with root K is K, N, O, and P. Consequently, the pre-order traversal of T is A, B, E, G, K, N, O, P, F, C, and D, and G, and then we have L, M, H, and I. We will now define in-order traversal. Let T be an ordered rooted tree with root R. If T consists only of R, then R is the in-order traversal of T. Otherwise, suppose that T1, T2, T of N are the subtrees at R from left to right. The in-order traversal begins by traversing T1 in order, then visiting R. It continues by traversing T2 in order, then T3 in order, and finally we have T of N in order. Figure 5 indicates how in-order traversal is carried out. Now let us take an example. In which order does an in-order traversal visit the vertices of the order-rooted tree T in Figure 3? The steps of the in-order traversal of the order-rooted tree T are shown in Figure 6. The in-order traversal begins with an in-order traversal of the subtree with root B, the root A. Then we have the in-order listing of the subtree with root C, which is just C, and then the in-order listing of the subtree with root D. The in-order listing of the subtree with root B begins with the in-order listing of the subtree with root E, the root B and F. Now the in-order listing of the subtree with root D begins with the in-order listing of the subtree with root G, followed by the root D, followed by H, and followed by I. So the in-order listing of the subtree with root E is J, followed by the root E, followed by the in-order listing of the subtree with root K. The in-order listing of the subtree with root G is L, G, and M. The in-order listing of the subtree with root K is N, K, O, and P. Consequently, the in-order listing of the order-rooted tree is J, E, N, K, O, P, M, B, F, A, C, L, G, and M, and D, and finally we have H and I. Figure 6 is showing the pre-order, the in-order, the post-order for this traversal tree. Let B an order-rooted tree with root R. If T consists only of R, then R is the post-order traversal of T. Otherwise, suppose that T1, T2, T of N are the subtrees at R, from left to right. So the post-order traversal begins by traversing T1 in post-order, then we go to T2 in post-order, then Tn in post-order, and ends by visiting R. In which order does a post-order traversal visit the vertices of the order-rooted tree T shown in Figure 3? Figure 7 illustrates how post-order traversal is done. Example 4 illustrates how post-order traversal works. The steps of the post-order traversal of the order-rooted tree T are shown in Figure 8. The post-order traversal begins with the post-order traversal of the subtree with root B, the post-order traversal of the subtree with root C, which is just C, the post-order traversal of the subtree with root D, followed by root A. The post-order traversal of the subtree with root B begins with the post-order traversal of the subtree with root E, followed by F, followed by the root B. Then the post-order traversal of the rooted tree with root D begins with the post-order traversal of the subtree with root G, followed by H, followed by I, and followed by the root D. Now the post-order traversal of the subtree with root E begins with J, followed by the post-order traversal of the subtree with root K, followed by the root E, and the post-order with root K is N, O, P, K. Therefore, the post-order traversal of T is J, N, O, P, K, E, F, B, C, L, M, and G, and H, and I, and finally we have D and A. There are easy ways to list the vertices of an order-rooted tree in pre-order, in-order, and post-order. To do this, first draw a curve around the order-rooted tree starting at the root, moving along the edges as shown in example in figure 9. We can list the vertices in pre-order by listing each vertex the first time this curve passes it. We can list the vertices in order by listing a leaf the first time the curve passes it, and listing each internal vertex the second time the curve passes it. We can list the vertices in post-order by listing a vertex the last time it is passed on the way back up to its parent. When this is done in the rooted tree in figure 9, it follows that the pre-order traversal gives A, B, D, H, E, I, J, C, F, G, K. The in-order traversal gives H, D, B, I, E, J, A, F, C, K, G. And the post-order traversal gives H, D, I, J, E, B, F, K, G, C, A. Algorithms for traversing order-rooted trees in pre-order, in-order, and post-order are mostly easily expressed recursively. So algorithm 1 is summarizing this. Note that both the pre-order traversal and the post-order traversal encoded the structure of an order-rooted tree when the number of children of each vertex is specified. That is, an order-rooted tree is uniquely determined when we specify a list of vertices generated by a pre-order traversal or a post-order traversal of the tree, together with the number of children of each vertex. In particular, both a pre-order traversal and post-order traversal encode the structure of a full-order emery tree. However, when the number of children of vertices is not specified, neither a pre-order traversal nor a post-order traversal encoded the structure of an order-rooted tree. Now let us discuss infix, prefix, and postfix notation, as they are very important for us to understand, especially with programming language. We can represent complicated expressions such as compound proposition and combinations of sets and arithmetic expressions using order-rooted trees. For instance, consider the representation of an arithmetic expression involving the operators plus, addition, subtraction and multiplication and division, and exponential. We will use parentheses to indicate the order of the operations. An order-rooted tree can be used to represent each expression where the internal vertices represent operations and the leaf represent the variable or numbers. Each operation operates on its left and right subtree in that order. So let us take an example. What is the order-rooted tree that represents the expression x plus y to the power 2 plus x minus 4 divided by 3? The binary tree of this expression can be built from the bottom up. First, a subtree of the expression x plus y is constructed. Then this is incorporated as part of the large subtree representing x plus y to the power 2. Also, a subtree of 4x minus 4 is constructed, and then this is incorporated into a subtree representing x minus 4 divided by 3. Finally, the subtrees representing x plus y to the power 2 and x minus 4 divided by 3 are combined to form the order-rooted tree representing x plus y to the power 2 plus x minus 4 divided by 3. These steps are shown in figure 10. An in-order traversal of the binary tree representing an expression produces the original expression with the elements and operation in the same order as they originally occurred, except for an array operation which instead immediately follow their operands. For instance, in-order traversal of the binary tree in figure 11, which represents the expression x plus y divided by x plus 3. And we have x plus y divided by x plus 3 and x plus y divided by x plus 3 all lead to the infix expression x plus y divided by x plus 3. To make such expression clear, it is unnecessary to include parentheses in the in-order traversal whenever we encounter an operation. The fully parenthesized expression obtained in this way is said to be in infix form. We obtain the prefix form of an expression when we traverse its rooted tree in pre-order. Expressions written in prefix form are said to be in Polish notation. An expression in prefix notation where each operation has a specified number of operands is unambiguous, so no parentheses are needed in such an expression. The verification of this is left as an exercise for the viewer. What is the prefix form for x plus y up to the power 2 plus x minus 4 divided by 3? We obtain the prefix form for this expression by traversing the binary tree that represents it in pre-order. Showing in figure 10 that this is produced plus to the power plus xy2 then divide minus x for 3. You can see the full expression in the slide. In the prefix form of an expression, a binary operator such as plus precedes its two operands. We can evaluate an expression in a prefix form by working from right to left. When we encounter an operator, we perform the corresponding operation with the two operands immediately to the right of this operand. Also, whenever an operation is performed, we consider the result a new operand. What is the value of the prefix expression plus minus star 235 divided to the power 234? The steps used to evaluate this expression by working right to left and performing operation using the operands on the right are shown in figure 12. The value of this expression is 3. We obtain the postfix form of the expression by traversing its binary tree in post order. Expressions written in postfix form are said to be in reverse Polish notation. Expressions in reverse Polish notation are unambiguous, so parentheses are not needed. The verification of this is left to the viewer. The reverse Polish notation was extensively used in electronic calculation in the 1970s. What is the value of the postfix expression 723 star minus 4 to the power 9 3 divided plus? The steps used to evaluate this expression by starting at the left and carrying out the operation when two operands are followed by an operator are shown in figure 13. The value of this expression is 4. In this video we have covered traversal algorithm, infix, prefix and postfix notation. Thank you for watching and see you in the next one.